to increase the temperature of a gas, we need energy. To be specific about how much energy we need a 1/2 nRT, and really that should be nR delta T. There should be a delta on this T, and a delta on this T, and a delta on this T. Delta here, delta here, and delta here. Those are pretty bad deltas, but at least you know what they are. Okay? We need a 1/2 nR delta T to increase the x component of the molecular average velocity. Okay, on the average, the molecules are moving at some velocity, and they're moving in the x direction, and then there's an independent y direction and an independent z direction. 3 independent directions in space. For the x direction, we need a 1/2 nR delta T. For the y direction, we need a 1/2 nR delta T. For the z direction, we need a 1/2 nR delta T. Now you see this in the billiard ball simulation, how the energies in the x and y directions just get mixed up. The total energy doesn't change. If all the energy is in the x direction, after a few collisions, it'll be equally partitioned between the x and the y directions. And if you have a third dimension, it gets partitioned into the z direction also. So that the energy gets equally distributed among x, y, and z directions, this much energy to each direction, as we'll see from the kinetic theory. In addition, if you happen to have a diatomic molecule like oxygen or nitrogen, there are 2 independent ways that molecule can spin and have a lot of energy. Okay? It could spin about the axis that's parallel to my fingers, like this, or it could spin about this axis. Okay? With the molecule in this position, it can spin about this axis or about this axis, and those axes are mutually perpendicular, so they're independent. There's no particular energy associated with turning around this axis. We have a diatomic molecule, mass on this side, mass on this side, not much in between. The energy comes from, or the energy goes into rotation about this direction and rotation about this direction. There are 2 such directions, one about what we'll call the x-axis, one about what we'll call the y-axis, although those labels are kind of arbitrary. That's for a diatomic molecule. So we see that the internal energy of a gas is made up of the 1/2 nRT for the x direction, for the y, and for the z direction, and the 1/2 nRT for the rotation about the x-axis and about the y-axis, if we happen to have a diatomic molecule. This energy here, the 3/2 nRT that we get for the x, y, and z directions, is called our translational energy. Okay? Translational internal energy. And let's zoom in on those names a little bit. So we have 3/2 nRT translational. For a diatomic gas, we have 5/2 nRT total for the 1/2 nRT for each of these degrees of freedom. In addition, if we have a constant pressure situation, we've got to add a 2/2 nR delta T. That's a picture of where the energy goes in a gas. So what happens when we add thermal energy to the system? We add a delta Q to a system consisting of a gas. Any gas gets its 3/2 nR delta T, translational, monatomic, diatomic, or anything else. This motion in the x, y, and z directions causes collisions with the container walls and is what causes pressure as a result of the momentum changes with the container walls. This energy here, the 2/2 nR delta T, for a diatomic gas, this is rotational energy and has no effect on pressure, because when a molecule hits the wall, it's as likely to be rotating toward the wall as away from the wall. So this has no effect on pressure. Now, this much energy gets added at constant volume. If you have a monatomic gas, it's just this, there's none of this. If it's a diatomic gas, it's both of these. But if you're increasing the temperature at constant volume, you have to add this much thermal energy depending on this, whether you have diatomic or monatomic. If you're adding at constant pressure, then you have another 2/2 nR delta T for the expansion, to do the work of the expansion. And that's where the energy goes in a gas. The adiabatic expansion, where PV to the gamma remains constant, gamma is your Cp over Cv. For a diatomic gas, then, Cv is 5/2 R. The 3 degrees of rotational plus 2 degrees of 3 degrees of translational plus 2 degrees of rotational freedom, and then another 2 degrees if you're doing constant pressure. If you do Cp over Cv to get gamma, it's going to be 7/2 R over 5/2 R, which reduces to 7/5 or 1.4. And that's the adiabatic gas law. Okay, and that's how you have the adiabatic expansion. We can put all this together now to analyze the energy transformations in the system we've been studying.